Okay, this is the matter and the gas laws review. Make sure you've got a calculator and your reference tables close by. Okay. Number one, the particles of a substance are arranged. Oh, by the way, you can hear my dishwasher in the background. I apologize. The particles of a substance are arranged in a definite geometric pattern and constantly vibrating. Definite pattern would have to be the solid phase. So nice and tight, packed together. Which phase change results in the release of energy? So this is exothermic, so giving off heat. So notice we all have H2O, it's just a matter of the phases. So H2OS, that's the solid, that's snow melting. So when snow melts, you have to take heat in. Number two, that's snow all the way to the boiling. So that's taking in heat going through two phase changes. Number three, this is liquid water on the stove boiling for pasta. And so the last one is taking a shower, that gaseous water vapor hits your cold mirror and forms condensation. So that is your answer for exo, giving off heat. As ice melts at standard pressure, its temperature remains 0 degrees Celsius until it has completely melted. What occurs with potential energy? So if we take a look over here, we have this phase change diagram. So 0 degrees Celsius, ice melting, that would be B to C. So it is completely melting. So that means this is the solid and this is the liquid. So this is the phase change. It says the temperature is 0 degrees Celsius until it's completely melted. So obviously the graph increases, although temperature does not. So potential energy will increase because that's what's going on while the graph is continuing. Number four, as electrical energy is converted to heat energy, what happens to the total amount of energy? That's the law of conservation, which states energy cannot be created or destroyed. An iron bar at 325 Kelvin is placed in a sample of water. The iron bar will gain energy from the water if the temperature is, okay, so you should remember that heat flows from hot to cold. So also, we're not dealing with apples and oranges here. Or we are dealing with apples and oranges. We've got Kelvin and Celsius. Let's make them all Kelvin. So 65 degrees Celsius plus 273 is going to be 338 Kelvin. 45 plus 2. And by the way, this is on the reference table. Let's take a look. Right here. Table T. To convert between Celsius and Kelvin. There it is, right there. Let's see. If the iron bar gains energy, it has to be higher. So the only one that's higher than 325 is 338, which is choice 3. Number 6. As the temperature of a sample of H2O liquid decreases, average kinetic energy of the molecules will also decrease. Those are synonyms, average kinetic energy and temperature. The temperature in a sample changes from 10 degrees Celsius to 20 degrees Celsius. How many Kelvin does the temperature change? Okay, so this is a tricky one. So 10 to 20, that is a 10 degree change, which means 10 Celsius, 10 plus 273 is 283, and this is 293. So it's also 10. You are tricked by thinking, I'm going to convert this, but that is wrong. It's just how many Kelvin does it change. So convert these both to Kelvin and then see the change. Endothermic means gain heat. And endothermic is solid to liquid to gas or solid straight to gas. Melting, that is solid to liquid. Okay, so that works. Freezing is liquid to solid. That's backwards. Melting is solid to liquid. Evaporating is liquid to gas. So that seems like that's our answer. Condensation is gas to liquid. So that gets rid of both of those. So it is indeed choice 2. As a solid is heated, its temperature increases from 10 to 25 degrees Celsius, remains 25 Celsius for 5 minutes, and then increases beyond 45 degrees Celsius. What can be drawn upon the sample? So I'm actually going to look at number 10 on the graph. So as a solid is heated, it goes from 10 to 25, remains at 25, and then increases to beyond 45. So since it remains 25, that would be its melting point. Melting point. You could also say it's freezing point, except for it's going from solid to liquid, but that is melting. So number 9 is choice 3. Here we are on 10. Let me erase this. The graph below shows a uniform heating of a substance starting below its melting point when the substance is solid. Which line segments represent an increase in average kinetic energy? That's temperature. So which ones show an increase in temperature? A to B, C to D, E to F. So A, B, and C, D. Choice 2. I'm not even going to keep going. A student obtained the following data while cooling a substance. The substance was originally in the liquid phase below the boiling point. So if we're going to look back here, it's liquid, like C to D. So let's take a look. So 70, 63, 57, 53 for a bunch, and then down. So seeing as we flatlined on 53, that's our answer. By the way, notice this is the opposite of this graph, just because this is a heating graph and that would be a cooling graph. The temperature of a sample of water changes from 10 to 20 degrees Celsius and water absorbs 420 joules of heat. What is the mass of the sample? So I would go back to my heat formulas and I'd say, okay, which one includes a change in temperature? Q equals MC delta T. If I'm dealing with water, which I believe I am, I need to grab the heat of a specific heat constant of water, which is 4.18 joules. So information you need is packed into the reference table. So I have Q is 420, M is what I don't know, C is 4.18, and delta T is 20 minus 10, which is 10. So let's see, 4.18 times 10 is 41.8, so 41.8 M equals 420. Divide both sides by 41.8. 420 divided by 41.8. Sorry, my calculator. What? Is 10.0 blah, 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 blah. So, choice 2. What is the amount of heat required to completely melt a 29.95 gram sample of H2O solid at 0 degrees Celsius? So, our keywords are melt, solid, and one temperature. So, coming back to here on the reference tables, I don't have a change in temperature. So now it says melting, so that would be heat of fusion. This is solid to liquid, and this is liquid to solid, to gas. So we want Q equals MHF. Now the HF constant for water is 334 joules per gram. So we're going to need that in just a second. So here we go. So Q equals mass, 29.95, and then melting, 334 joules per gram. So 29.95 times 334 is 10,003.3. That's not a choice. But you know what? These numbers are big. 3 and 4 are big, so that's not. Now, these are the constants. They tried to trick you with 1 and 2. So then the question is, which of these answers is this? 10,000 would be 1, 2, 3, 4. 10 to the 4th, so choice 4. Choice 4 for number 13. Heating curve. Between which times could the heat of fusion be determined? Heat of fusion is between solid and liquid, melting and freezing. That's B and C. So choice 2. An 80-gram sample of water at 10 degrees Celsius absorbs 1680 joules of heat. Oh, final temperature. Okay, getting into this. This is Q equals MC delta T. However, we need to change delta T to T final minus T initial. So let's see. 1680 equals 80 times 4.18 times T final is what we're looking for. So TF minus 10. All right, so that's pretty messy. I'll try to clean it up. 80 times 4.18 is 3. Where can I put it here? Put it up here. 334.4 times TF minus 10 equals 1680. So let's divide 1680, both sides actually, by the 334.4, and you get 334.4, 334. You get 5.02, etc. equals TF minus 10. Add 10 to both sides. It's going to be 15.02, which rounds to 2, which is 15.0. You got to clean that up. Okay. How many joules of heat energy are released? Okay, so again, we got a delta T. Q equals 50, 4.18, 70 minus 60. So technically, T final minus T initial would be negative 10. We could account for that because the word released. So none of these answers are negative, but, you know, the word released would mean given off exothermic. So 50 times 4.18 times 10 or negative 10 is 2400, which is, what did I do wrong? I should get 2100. What did I do wrong? 50? Oh, oops, I wrote 4.8. 50 times 4.18 times 10. Yeah, it's 2090 is what the calculator gives you, so round it to 2100. What is the total number of kilojoules of heat energy absorbed in the temperature of 200 grams? Okay, so looking for heat energy, Q equals 200, 4.18, and the temperature change is 30. 200 times 4.18 times 30. So we get 25080. Now that's joules. So to go to kilojoules, it's going to be 1, 2, 3 spots, 25.080 kilojoules. So I'm going with choice 3, even though it's a little off. There's probably some rounding, or 25.1 instead of 25.2. I don't know. Clean that up. At 1 atmosphere pressure, water and ice can exist at equilibrium at a temperature of. So, okay, so what temperature is the freezing point and the melting point of solid to liquid? So that would be 0 degrees Celsius. They're going to try to trick you with 3, and that's not the answer because they want you to know 32 degrees Fahrenheit, and that says Celsius. As a solid substance absorbs heat at the melting point will, it's a point. It won't change. It's 1 point. The heat required to change 1 gram of a solid to a liquid. Solid to liquid, that's heat of fusion. Heat of fusion. For number 20. Heat of fusion, we just did this one. Solid to liquid. Okay, so at 1 atmosphere pressure, 25 grams of a compound at the normal boiling point is converted to a gas by addition of this. Heat of vapor. Okay, so now we're actually looking for a heat of vaporization. And so we're not going to be looking at the front because this is what we're going to be calculating. It says a compound. It's not necessarily water. So 34400 equals 25 times X. So 34400 divided by 25 gives me 1376. That's our answer. Sublimation, this is something we just need to memorize. Solid straight to the gas. So this is dry ice right here. Which phase change is accompanied by the release of heat? Release of heat is exothermic. That's gas to liquid, liquid to solid, or gas straight to solid. So that would be choice 4. Is liquid water freezing into an ice cube. Excuse me. All right. Number 25. Which substance has the lowest vapor pressure at 75 degrees Celsius? So this is table H. Here we go. It says, which substance has the lowest vapor pressure at 75 degrees Celsius? So I'm going to erase this because I don't know what that is. 75 degrees Celsius is here. Vapor pressure is here. The first line we hit is ethanoic acid, so I'm guessing that's my answer. It is 25. That's 2. Based on table H, which sample has the highest vapor pressure? So water at 20, 80, ethanol at 50, or 65. Hold on one second. I'm going to just, because I have this as a paper, it's going to prevent me from going to have to. Okay, so back to table H. All right, so get rid of this. So it says Water at 20. So water is this third curve, water at 20. The x-axis goes by 5 degrees. So this is water. That's pretty low vapor pressure. Water at 80. Here's water at 80. Ethanol at 50. Ethanol is the second curve. And then ethanol at 65. 65 ethanol. So it looks like that's the highest of the vapor pressures, because again we'd come over here to the Y. So back to that. So we're going to go with ethanol at 65. Yep. Normal boiling point of 4 compounds. Which compound has the strongest intermolecular forces? Okay, so the stronger the force, the longer it's going to take to boil, which means the higher the boiling point. So you want the highest boiling point. That is choice 1. All of these are negative, negative, negative. So you want the highest, because it takes the most heat to boil because the forces are so strong. 2 basic properties of the gas phase. They do not have definite shape. That's how you can have fun shaped balloons. So no definite shape, and also no definite volume, because they take the volume of the container. 29 is review. Equal volumes of those 2 different gases at STP contain the same number of molecules. This is Avogadro's hypothesis. Oh boy. Yikes. Just needed some water there. Hydration. All right, number 30. The behavior of a real gas would be most similar to an ideal gas under conditions of the beach. When do you want to go to the beach? High temperature and low stress, low pressure. So high temperature, low pressure is choice 3. Number 31. At the same temperature and pressure, 1 liter of CO2 gas and 1 liter of CO gas, carbon monoxide, and 1 liter of CO2 gas have, this again is Avogadro's hypothesis. So they would have the same number of molecules, but they have the same volumes. So it could be 3. They don't have equal masses because this is 2 oxygens and this has 1. So it's got to be choice 3 for number 31. Okay, now we got some gas laws questions here. The pressure on a 200 milliliter sample of CO2 at constant temperature is increased from 60 kilopascals to 120. What's the new volume? So we've got changes in pressure and volume, but not temperature. So let's go back. Changes in pressure and volume, but not temperature. So here I am, the gas laws. Combined gas law. Pressure and volume are changing, but not temperature. If temperature is constant, I get rid of it. So there's my formula. P1 times V1 equals P2 times V2. Just for kicks, that's called Boyle's law. But you didn't need to know that. Whatever is constant, you can just eliminate from the question. So 20, and then it says 20 milliliters, and it's at 60 kilopascal. And now it's at 120 kilopascal, and I don't know the new volume. So there are 2 ways to do this. One, you just plug it into your calculator, totally just algebra. The other is, take a look at what happened to the pressure. The pressure is doubled. So this is an inverse relationship. If the pressure is doubled, the volume is halved. It should be half. I'm guessing it's choice 1. Let's just do it. So 60 times 200 is 12,000 equals 120 times x. So 12,000 divided by 120 is indeed 100. So you can, kind of go with your gut here, but calculator always helps. 33. A gas has a volume of 1,400 milliliters at a temperature of 20 K and 1 atmosphere. Okay, so I see volume is changed. We're going to have temperature change and pressure. So this is combined gas law. So in this case, we're going to need it all. We're going to need everything. So P1 V1 over T1 equals P2 V2 over T2. And remember, temperature is always in Kelvin, because you cannot have temperatures like 0 degrees as our denominator. That's undefined. So we'll try to squeeze it in. 1 atmosphere times 1,400 over 20 we're looking for a new volume, so we have 0.5 atmosphere, 50. Don't know volume, and our temperature is 40. So I'm going to cross multiply. That's what I like to do. You know, it's algebra, so 1400 times 1 times 40 is going to be 56000 equals 20 times 0.5 times our x, so 10x. So 56000 divided by 10 gives me 5,600 milliliters. Choice 4. It must be 4, sorry. All right. Number 34, what volume will 300 milliliter sample of a gas at SCP occupy when the pressure is doubled at constant temperature? Constant temperature means we're dealing with Boyle's law again, so I'm going to work down here. So 300 is our first. It doesn't even give us numbers, so let's just choose. How about 1 atmosphere? And so it's doubled, so it's 2 atmospheres. So I don't know. So you could do something like that, or you could say, hey, if the pressure is doubled, the volume is halved. So that's got to be 150. At constant pressure, the volume of the gas will increase and the temperature is changed from, okay. So constant pressure means, let's go back. If pressure is constant, that's Charles's law. V1 over T1 equals V2 over T2. And again, temperature must be in Kelvin. So I'm going to erase this here, give ourselves some room. So again, 10 degrees Celsius is not appropriate. We need 283 Kelvin. So 283 Kelvin, and it says at constant pressure, volume increase. So, okay. So if we want, this is Charles's law, and it's a direct relationship. So if the volume of the gas increases, whatever it is, you're going to have to increase this too. So you need something higher than 283. And the only thing higher than 283 is 293. So that's our answer. So that's not neat and tidy, but you know. Which gas will diffuse at the fastest rate under the same conditions of temperature and pressure? This is Graham's law. This is not on the regions. This is honors only. And it says that the heaviest gases will diffuse the slowest. The lightest gases will diffuse the fastest. And so we need to check molar masses as found on the reference table. So let's do it. So again, sorry, this is on the side. So O2, I had other stuff written here. O2 is 16 times 2, so 32. N2 is 14 times 2, so that's 28. F2 is 19 times 2, so what is that? 38? It's late. I'm going to use a calculator. It is. And then H2 is 1 times 2, so that's 2. So the heaviest is fluorine and the lightest is hydrogen. So it says which will diffuse the fastest. That's going to be the lightest. So that's going to be choice 4, hydrogen. The table below lists 4 gases and their molecular mass, which diffuses the slowest, so the heaviest. So it's got to be D, because it's the heaviest. Which gas would diffuse most rapidly? Heaviest. D. Oh, sorry, hold on. Oh, no. I read it too quickly. Diffuse most rapidly means the lightest, fastest. Slow and heavy, quick and light. So sorry about that. So we want the fastest, so that's the lightest. By the way, molecular mass of 4, isn't that helium? All right, let me erase this. The diagram below shows 2 flasks connected by a stopcock or a valve. Get over it. Flask A contains helium gas. B is a vacuum, meaning there's nothing there. What is the final gas? What final volume will the gas occupy after the stopcock is open? So when this opens up, everything will diffuse. So if you've got 500 total milliliters of space, that's what the helium's going to take up, is all of it. So this is Dalton's law of partial pressure, meaning if you've got this and this, it's going to take it all up. Number 40 is also Dalton's law. It's not on the reagents anymore. The partial pressures of gases A, B, and C in a mixture are as follows. What is the total pressure? You just add them up. 0.750 plus 0.250 plus 1.25 gives me 2.5. That's not a choice. 2.5 atmospheres. Oh, silly. And then they want kilopascal. That's easily acquired. 1 atmosphere is 101.3 kilopascal. You can find that right on the front of the reference table, table A. So 2.5, see, I read too fast, 101.3. So that gives me 253.25 kilopascal. So, that's still not quite right. What did I do? It should be choice 3, according to the answer key, but let's see. Did I add wrong? 0.75 plus 0.25 plus 1.25 is 2.25. Oh, there it is. This is 2.25 atmospheres. There we go. 2.25 times 101.3 gives me 227.925. So it's 220. Yes, there it is. Yeah. See, it's too late at night. Look at it. You can't even see it. Look at it. See, it's 9:26. I'm getting old. If you have any questions, please reach out. Otherwise, good work. Thanks.